So from the 2010 Scholarship Physics paper, question 6a, if a light object with a small mass and a heavy object with a large mass have the same kinetic energy, explain which of the two has the larger momentum. So the kinetic energy formula, not that we're just jumping straight to formulas, but we just write down bits of information that are useful to us. So EK equals half mv squared, momentum is mass times velocity. Okay, so let's just separate those because we are going to have to do some calculations. Don't want to mix them up. So we need a little bit of notation here. We might use large M for our large mass, so we'll call that a capital M, and that's going to have a small velocity if it's got the same momentum, and our small mass is going to have like a rounded top, small m, and a larger velocity. It makes sense that that's the case if we're looking at the same kinetic energy, but different momentum. One of them will have to have larger mass and smaller velocity, and the other has to have larger velocity and smaller mass. Anyway, so let's go ahead and get on with the question. Explain which of the two has the larger momentum. We could rewrite these equations in terms of these big M's and small m's and large V's and small V's to give us a sense. They have the same kinetic energy, so we know that half small m large V squared is going to equal half large M small v squared. Okay, so that's one equation we have. We've also got the momentum equation, so the momentum of the large mass, we'll call that like a capital P, is going to be large mass times small velocity, and the momentum of the small, we'll use rho as sort of a small p, momentum of the small mass is going to be small mass times large velocity. Okay, what we would like to do to see which has the larger momentum is compare these two in some way. At the moment they can't be compared because they have two different variables, big M and big V and large small v. We need to have the momentum given in terms of the same variables, or at least close enough that we can see if one of them has a larger different part. Okay, like a larger coefficient, and then we'll see which one has the larger. Let's go ahead and see if we can use this momentum equation, the equated kinetic energies, to see if we can substitute in a rearrangement for probably that large V over here, and see what we do. Anyway, we'll do it. I'll go ahead. I'm rambling a little bit because I'm tired. So let's make large V the subject. A relatively quick rearrangement is going to be square root of all of that. Okay, we've divided by M, we've square rooted, and we can also change that just a little bit, so it's square root capital M over little m, and then we've just taken the V squared square root out and make it just plain V, which is fine. And it's very hard to go over the top of things on an iPad that you don't have a proper stylus for. Anyway, so we can substitute this into here for the momentum of the small mass. Let's just do that. So small momentum equals M small v square root of large M over small m. Okay, we're going to have to zoom in a little bit. We can reduce that down just a little bit because this part here, 1 over square root m, is equal to m to the minus half. Okay, and this m here is m to the power of 1. So we're multiplying those two together. M to the power of 1 times by 1 over square root m, or 1 over, or m to the negative. That equals m to the half, which is square root m. Okay, so we can rewrite this as small momentum equals square root m times velocity times square root large M, which means we can we can rearrange it just ever so slightly to put the V. In fact, let's just do that by scribbling. Put the V over here, and then what we can see now is we've got the small momentum in terms of a coefficient times V, and if we go back up, that's what we've got here for the large momentum, a coefficient times V. Well, there's a coefficient. So we want to compare the two coefficients and see which is the larger. And that will tell us which has the large momentum. So one of them has a coefficient of square root, we'll just put these under the same square root. That's one coefficient, and the other coefficient is just plain old m. Okay, and this was for the large momentum, and this is for the small momentum. So which of those is the larger coefficient? We need to, there's a couple of ways we could do this. Okay, I like this option, and that's just to square both sides to get rid of that square root. So that'll give us small m, large M, and on the other side it's going to go to m squared. So we've done the same operation by just call it x to the power, we've squared it. Same operation, so we haven't modified the ratios. Well, ratio is probably the wrong word, but we haven't modified the which one's going to be larger, that sense of it. But we can straight away see on the right hand side it's capital M times capital M, but this is small m times capital M. So clearly the momentum for the larger mass is going to be larger. There's one other way that you could do this, and that is to look at a way what you would have to multiply the left hand side by to reach the right hand side over here with the capital M, and then see if that number is less than 1, and that would tell us, if it was less than 1, that this is in fact smaller. The smaller momentum is smaller mass has a smaller momentum. If the number you're multiplying that side by to get to there is less than 1, and it is less than 1, we can see that we've got square root m, so we need to divide by square root m. Let me just bring you down a little bit here. So square root small m large M, we have to multiply it by something over square root of m, because that'll cancel out the small m, and we have to multiply it by square root of large M on the top, because that'll just leave us with m on there. And so the question then is this greater than 1? And the answer has to be yes, because this here is a larger mass than this. So that means this whole number is going to be larger than 1, which means you're increasing the left hand side, the small momentum coefficient, to get to the same value for the right hand side, which means right hand side is larger. Okay, stated that over and over again. There you go.